Welcome to my new calculus channel. My name is John Gabriel. In this video I'd like to discuss the representation of numbers in radix systems. So there is a common knowledge in the mainstream that states that if a radix representation, a non-terminating, let's write that down, a non-terminating radix representation repeats itself, if it repeats, then this implies that the limit is a rational number. Okay, the limit is a rational number. If, however, it does not repeat, then this implies that the limit is an irrational number. Okay, so this is something that's generally agreed to in the mainstream. But now let me show you an example here of a special kind of prime number, and in fact this property is held by all prime numbers. It's the property that the remainders are mapped to the representation that you see which repeats. So for example, 1 is mapped to 1, 3 to 4, 2 to 2, 6 to 8, 4 to 5, and 5 to 7. Every prime number has this property, this special mapping. Okay, so doesn't matter which one you use. If you have 11, then you'll have the remainders 1 to 10 being mapped to a single digit. And it doesn't matter how big the prime number is. It can be trillions of digits long. All the remainders will map to a single digit. Now suppose I give you a prime number, or suppose I give you a radix representation that is 2 trillion digits long. Okay, 2 trillion digits. Right. Now, you'd have to basically show me how you would determine whether that's rational or irrational. If you get to the end of 2 trillion digits and you have not found a limit, or that it repeats, you may be tempted to think it's irrational. But that may not be enough, because if you don't know, for example, if I gave you n trillion digits, you don't know how far you would have to look in order to determine whether it's a rational number or irrational number. So if it doesn't repeat, you really don't know, unless you actually have a particular fraction in the form of p over q, and then you know that of course that can either repeat or not repeat. But there is no such thing as an irrational number. That's just a myth. There is an incommensurable magnitude which is really supposedly thought of as a limit, but a magnitude is not a number. Okay, and in fact a number is the measure of a magnitude. Now when you find a pattern that repeats for a certain fraction like this, the repeating pattern is a property of the fraction, okay, of the fraction, not the other way around. A fraction is not the property of a repeating pattern of digits in any radix representation. So there's really nothing fantastic about this approach here, and it doesn't actually tell you for sure what is an irrational number, except that all you know is that it does not repeat. Well, so what? If I gave you n trillion digits, you wouldn't be able to tell me if it repeats or not. By getting to the end of these n trillion digits, if you didn't find a pattern, you couldn't tell me that it's irrational, because you wouldn't know unless I told you that was the end of the n trillion digits. And so there is this contradiction in mainstream mathematics where mathematicians think that this here is a proper representation of 1/7. It's not. While the limit of this series here is equal to 1 series is equal to 1/7, the limit of these repeating terms is 1/7, this here is never equal to 1/7, just as 1/3 is not equal to 0.333, etc., because 1/3 is not measurable in base 10. And you can, of course, get to understand this a little bit better if you consider the digits that are supposedly representing pi. So, for example, it doesn't matter how many digits of pi you give me, to how many n places. I can find another radix representation with the same digits, exactly the same digits in those n places that is not pi. In fact, I can find innumerable numbers with the same digits in the first n places. And that doesn't mean that the number is irrational, okay? It doesn't mean that the number is irrational. Just because you haven't been able to find a pattern doesn't mean it's irrational. Most of the proofs of these so-called incommensurable magnitudes, such as pi, e, square root 2, etc., are not derived by looking at the non-terminating radix representation. They're actually proved in very different ways. So you can actually prove that this here is an incommensurable magnitude. Same with e, same with pi. Okay, you can prove that these are incommensurable magnitudes, but you cannot say they're incommensurable magnitudes because the digits do not repeat. That's just nonsense. Alright, so just to summarize here, a repeating pattern is a property of a fraction and not the other way around, okay? Not the other way around, because it may not be a fraction. You get that? In the case of pi, it's not a fraction. It's a ratio of magnitudes. It's the ratio of the circumference to the diameter, right? And these here may or may not be numbers. Well, at least one of them has to be irrational, or both can be irrational. But that, when I say irrational, I mean incommensurable, because incommensurable is not the same as irrational. An incommensurable magnitude literally means a magnitude that has no common measure with any other magnitude, in particular the unit which is used to measure all magnitudes. So if a magnitude cannot be measured by the unit, then what you have is not a number, only an approximation or an estimate, as you have in the case of pi when you write 3.14159 ... That's not pi. That's just nonsense. Okay? So this video is meant to expose this ridiculous notion that this here is somehow a property, or somehow a provable property that is propagated by the idiots in mainstream academia. This second part here, by the way, is not, in fact it's not even falsifiable. The first part is falsifiable, but the second part is not falsifiable, because you can never tell for certain when a given representation repeats or doesn't repeat. There is no way to determine that, okay? So this second part here is absolute rubbish, yet it's one of the requirements in determining whether a number is rational or irrational. This is the kind of nonsense that you have to learn in the mainstream mathematics, which I call mathematics. So I hope you've enjoyed this video, and that you'll join me again next time for another interesting topic. This is a new calculus channel, and my name is John Gabriel. Till next time, goodbye.